Okay, so the next topic in section 7.7 it has to do with similar triangles, right? Similar triangles. And so, but before we try to answer this question, I guess we should say what similar triangles are, right? So here's an example of two similar triangles. That looks a little better. So they're triangles that sort of look the same, but one might be bigger than the other. And what's the same about them are the three interior angles. The three angles are equal, right? But the sides don't have to be the same. So if we say the three sides here are, let's say, A, B, and C, right? And that's a B, sorry. And the sides here might be, let's say, C, D, and, or no, can't use C again. So how about D, E, and F? Okay. So obviously A does not have to be D, even though they're the corresponding sides. What has to be the same for each of these are their ratios, right? So the ratio of A to D has to be the same as the ratio of B to E, and it has to be the same as the ratio of C to F. C to F. Okay, right. So similar triangles, their ratios of the corresponding sides are equal. Okay. So I think we can use that to answer the following question. We have a student who measures the length of the shadow of a tree to be 42 feet. So, okay, without getting, right, this is my tree here. Okay. Right. Lovely tree. And here's the ground, right? And we have the sun, of course, focusing its rays, right? And we have the shadow, which, well, I don't know what color I should draw the shadow. How about purple? Right. So that's the length of the shadow. How about S for shadow, right? And how about the height of the tree? We'll call that H. Or let's just call it T for tree, maybe. This is the tree here. So this is how tall the tree is from here to here. All the way to the ground. Okay. Right. Now, there's a separate part of this. We have a 2-foot tall stick sticking out of the ground. So let's say this stick here is 2 feet tall. Right? And the 2 feet casts a shadow of, hang on, put the 2 over here. So, right, so the sun's rays create a shadow here. The shadow will also be purple, right? And this is the shadow of the stick. The shadow of the stick is 1.6 feet. So this here is 1.6 feet, right? The stick is 2 feet tall. Obviously, this is not to scale, right? This is, this is further along in the day, so I have the wrong scale here. Regardless, it doesn't matter the scale. The idea is that the ratio, the 1.6 to this S here, should be the same, right? So what I should get for an equation is the following. If I take the ratio of S, this side, to this shadow to this shadow, it should be S over 1.6, right? And the corresponding height of the tree is T, right? And the corresponding height of the stick is 2, right? So, yeah, so we know that the length of the shadow here, so what I'm using for S, we were actually given that. I should have just labeled that as 42 feet, right? So as it turns out, I can actually replace S with just the number 42. Sorry for having to erase that, but this is just 42, right? And so this is our proportion, right? We should be able to solve for T, which is the height of the tree. So if the question is how tall is the tree, solve the equation and you get your answer, right? So again, cross multiply, right? 1.6 times t is equal to 2 times 42. Right. And 2 times 42 is 84. So if 1.6 times t is equal to 84, you just divide both sides by 1.6. Right? And again, use your calculator. 84 divided by 1.6. I get 52.5. So 52.5 should be the height of the tree. That's in feet, right? That's in feet. So that's how tall the tree should be. Again, if it looks wrong, if it looks like this should be shorter than 42, that's because I drew the wrong picture here, so this is also wrong. But again, this should just give you the idea of relating the sides of a triangle when you have similar triangles. Okay? So, yeah, so the answer, how tall is the tree? The answer, 52.5 feet. And I said in the previous problem that, you should round to the nearest whole number, but we can take half of a foot, right? That's just 6 inches. So we can also report the answer as 52 feet, 6 inches. But let's not be picky about that, right? Let's just leave this as 52.5 feet. That's good enough, right? Okay, so let's go on to our next example. We have a boat travels 57 miles downstream in the same amount of time it takes to travel 39 miles upstream. If the speed of the current is 3 miles per hour, find the speed of the boat if there was no current. And just to remind you that when there's no current, the book calls that still water. So find the speed of the boat in still water. Same thing. Right? So on a lake, for example, where there's no current, right? The water is pretty calm, pretty still. So when it's traveling downstream, it's traveling down a river, right? Right? And in this problem, they give us the speed of the current, right? So this may remind you of problems we did earlier where we had to find both the speed of the boat and the speed of the current. Here, fortunately, they give us the speed of the current. So the speed of the current, C if you will, is really just 3 miles per hour, right? So, yeah. So instead, we're looking for B, right? Let B, this is the speed of the boat. Speed of the boat with no current. So that's what we're looking for here, right? So this is another speed, time, and distance problem. So I should remind you, of course, that distance is speed times time. So speed multiplied by time is just distance. Hopefully you know that by now because we've had to use that before in similar problems, right? And so I think we can do the same type of thing that we did way back in, I believe it was chapter 4, where we made a little table here. Move it down a little bit here. Well, I should have moved that over a little bit, but that's fine. I'll just copy it down. Okay, so we have, again, 2 rows, 3 columns. Right, the columns, of course, are just speed, time, and distance. Time, distance. Right, and the 2 rows, if you remember, are not with the current, without a current, but with the current, so downstream, and then going against the current, which is upstream. Right, so this is downstream, with the current, so with current. And then upstream is not without a current, it's against the current. We're fighting the current, going the other way. Right, and so now what's the speed of the boat going downstream? Well, if there's no current, the speed of the boat is just B. The current is pushing it faster by 3 miles per hour. So it's going 3 miles per hour faster than the boat ordinarily would be going on a lake with no current, right? Make sense? Right? So just reverse it. If you're going upstream, you're going slower. You take the speed of the boat and then subtract the speed of the currents, which in this case is still 3, right? Okay. Now, how long did it take to go down the river? Well, they don't tell us that. They really don't tell us that at all. That's interesting. So for now, we don't know what this is. Let's just call it T for time. Right? So we don't know they don't tell us directly what that time is. However, notice that they do say that it's the same amount of time going both ways. So whether you're going upstream or downstream, it's the same amount of time. It's both T. Okay? All right, so hang on to that thought for now. The distance, however, is different. If you're going downstream, right, downstream you're going 57 miles. That's the distance, miles, right? And what about going upstream? Upstream, that was 39 miles, right? So, yep, going upstream, we're only going 39 miles. And that makes sense because in the same amount of time, we're covering less distance because we're going against the current. Presumably, we're going slower, right? Okay, so we have our two equations here, right? The first equation is just speed times time equals distance. So b plus 3 times t is equal to 57. And the same thing is true here, right? Except it's b minus 3 times t is equal to 39. Right. Now, if you're wondering how am I going to solve this, because I have, b and t here, I have two variables. Remember, you also have two equations. We also have two equations. So we have two variables in two equations. It just, whether you call them x and y or b and t, it doesn't matter, right? We should be able to solve this using the techniques from Chapter 4. So here's how I'm going to do it. I'm going to divide both sides of this by b plus 3. Right? And down here, I'm going to divide both sides by b minus 3. Right? So what that does effectively on the left here is that cancels the b plus 3 and the b minus 3. So what I'm left with here is that t, oops, hang on. Let me use the same color here. That t is equal to 57 divided by b plus 3. Right, that's a t. So for the second equation, I get the same t is equal to 39 divided by b minus 3. But remember, it's the same t for both. So these t's are equal here. That means these have to be equal. So that's our equation. We have 57 over b plus 3. I'll put that on the left, right? So that's the left. And then this will be the right side. Remember, these are equal here. So 39 divided by b minus 3. Okay. So that's our equation. If we solve that, we should be able to find the answer to the question we're looking for is what is b? What is the speed of the boat without a current? Right. All right. So yes, that's the hard part, is getting the equation, right? You get the equation by making the table, making this little chart here, getting the equations, and then doing this little trick, eliminating the t here, because we don't really care what t is. We don't want to know how long it takes. We want to know how fast the boat is going, right? Okay. Well, we have our equation, right? So at this point, this is a proportion. We have a fraction on the left, right, and a fraction on the right. So why don't we just cross multiply? Right? So multiply b minus 3 times 57, b minus 3 times 57, and that has to equal 39 times b plus 3. Okay. Well, why don't we just distribute the 57 here. This is going to be 57 times b minus 3 times 57. Right. Oops, 3 times 57. And that has to equal 39 times b plus 3 times 39, or 39 times 3, same thing, right? Okay. So 57 times 3 is 171. So hang on, this is still 57b minus 171 equals 39 times b plus 3 times 39, I want to say 117. Yep, 39 times 3, 117. Just checking on my calculator, right? Okay, so I think you can take it from here. This is just a straightforward linear equation, right? There's no b squared. So we should be able to solve this for b fairly easily. So we can isolate the b on both sides, on the left, let's say. So we can subtract 39b from both sides. Right. And if we do that, 57 minus 39 is 18. Right, I think it's 18. So 18 times b, right, minus 171 is equal to 0b plus 117. Okay, now we want to bring the negative 171 over, so we'll add that to both sides, plus 171. And now on the left, we're left with 18 times b, right, plus 0, equals 117 plus 171. So I'm guessing 288. Well, I'm not guessing, I'm adding them. I'm just want to make sure. I think that's right, 288. And so now, since I'm running out of space here, let me just go clear up here. So we still have 18 times b equals 288. Now just divide both sides by 18. And on my calculator, 288 divided by 18 is 16. So that tells me that b should be 16. What does that mean, right? So that solves the equation. You can check by plugging that back in. But let's think about what was b here. B was the speed of the boat with no current. So the question is, right? The question was, find the speed of the boat if there was no current. And now we have our answer. B is the speed of the boat with no current. So the speed of the boat with no current is 16. But remember, distance is in miles, so 16 miles. And time was in hours, so 16 miles per hour. So that's the speed of the boat without a current, right? And you can abbreviate miles per hour the usual way. MPH is fine too. So personally, I am not picky about that. Right. So, yeah, 16 miles per hour. That's the speed of the boat if there was no current, right? So to recap, right, just you read the problem, right? You realize that we're talking about distance and time and speed. So speed times time equals distance. You make your little table. You know, one row is for downstream, one row is for upstream. In problems where you have airplanes traveling with the wind and against the wind, right? So downstream is with the wind, upstream or well, I think they call it a headwind or tailwind. So going against the wind is with a headwind, going with the wind is with a tailwind. Either way, right? That's the corresponding plane problem, right? So it's very similar to a boat problem. Instead of a boat going down a river, you have airplanes traveling in the same direction as the wind or going against the wind. So same type of problem as this. So I hope that helps. Okay, so I think I'll do one more type of example in section 7.7. These are sometimes called work problems or work applications. You have either people working or computers are working or you have people painting houses. You have pumps that drain pools or fill pools. So those are the types of problems the type of work we're talking about here, right? So here we have this example here. If Tina mows the lawn by herself, it takes 4 hours. If Bill mows the lawn by himself, it takes 5 hours. To the nearest minute, how long would it take them if they worked together? Okay, so you might have seen problems like this before, and these are notoriously kind of tricky and difficult, right? So it's not necessarily obvious, right? But the way to think of it is, right, you have Tina mowing the lawn and taking 4 hours. Bill, if Bill mows the lawn, takes 5 hours. So how long would it take if they worked together? Well, a lot of people would guess 9 hours, right? 4 plus 5. But that doesn't make any sense, right? If it takes Tina 4 hours to mow the lawn by herself, you would think, right, if you get help, if somebody works with you, assuming that they have their own lawnmower, right? If you both use different lawnmowers and you need different parts of the lawn, by working together, you should take less time, right? If you work together and it takes more time, you're doing something wrong, right? It should take less than 4 hours if they both work together. It should certainly take less than 5 hours, right? So this is where you have to be careful. You don't add the amount of time in problems like this, right? What you add is something a little more tricky. It's a concept called the rate of work, right? It's how quickly you're working, right? So basically, it's the amount of job you do, right? It's the amount of work you do, right, divided by the time, how long you take to do that job, right? So that's what's called the rate of work, the amount of work divided by the time. Okay, it's not the time you add, it's this. So here's the idea, right? Let's draw the lawn here. So suppose you just have a nice rectangular lawn. I know that's not very practical. Lawns are more complicated than that. And we want to mow the lawn, right? So the idea is, if Tina were to mow the entire lawn by herself, well, if it takes 4 hours to do the entire lawn, let's say we just cut it in half and only do half the lawn. How long would that take? Well, half as long, right? Half of 4 hours is 2 hours, right? Now, suppose we cut that in half and only did a quarter of the lawn, right? So we divide this lawn into 4 parts: 1/4, 1/4, 1/4, 1/4. Oops, 1/4, right? So if you only do 1/4 of the lawn, right, that should take you 4 hours divided by 4. It should take you 1 hour to do each quarter. So 1 hour for each quarter of the lawn. And if you do 4 of those, you do 4 hours, right? So the amount of work for Tina, right, is 1 lawn in 4 hours. So this is Tina's rate of work, right? It's 1/4 of the lawn, of the entire lawn, per hour. For each hour that she works, she mows 1/4 of the lawn. Makes sense? Now, what about Bill? Well, Bill turns out to be a little bit slower, right? Because Bill takes 5 hours to do the entire lawn, right? So here's the lawn. And so what would Bill's rate of work be? Bill's rate, right? So if it takes 5 hours to do the entire lawn, you can imagine that in 1 hour, you only do, about 1/5 of it, 20%, right? So 2/5 in 2 hours, 3/5 in 3 hours, 4/5 in 4 hours, 5/5, 5/5, which is the entire lawn, in 1 hour, right? So each 1/5 of the lawn, each 20% of the lawn is mowed in 1 hour. So 1/5 of the lawn per hour. Okay, so that's Bill's rate. Bill works at a rate of 1/5 of the lawn per hour. Okay, so with that out of the way, now we should be able to at least get some idea of how to answer the question, right? So this is sort of the tricky part, is figuring out the rate of work. Once you have that, the rest of the problem shouldn't be that hard. Okay, and we're going to do it in much the same way that we did the previous problem, by using a table here, right? So just draw your 2 rows, 3 columns, as usual. Okay, so this is rate times time. So be careful. This is not, your rate is kind of the speed. It's how fast you're working, but it's not how fast you're actually traveling. it's the rate of work, right? So this is rate of work, how fast we're working, right? So if you multiply the rate of work times how long you work, you get the amount of the job that you do, right? In other words, this is the fraction of the lawn that gets mowed. This is the part of the lawn, fraction of the lawn that is completely mowed, right? Yeah. Okay, so it's basically the amount of work, how much work gets done as a fraction of the total lawn. Makes sense? Okay, so we only have two people working, right? We have Tina and Bill. So we already know Tina's rate of work, right? That's the 1/4. So we calculated that earlier. That was 1/4. Again, we get 1/4 because it's 4 hours for the entire lawn, 1/4 of the lawn each hour, right? And Bill's rate of work was 1/5. So 1/5 of the lawn per hour. For each hour that goes by, Bill mows 1/5 of it, right? Okay, so how long does it take if they work together? Well, that's the amount of time. That's what we don't know, right? So again, I guess I'll use capital T for time. So let T be the amount of time they work together. Be the amount of time, oops, sorry about that. The amount of time they work together. Work together. Forgive my sloppiness. And this is in hours, right? This is in hours because, this is reported as, 4 hours for Tina, 5 hours for Bill. So we'll do this in hours. Right. Oh, how do I know it's the same for both? Well, they work together. So if they work together, we're assuming they start at the same time and then they finish at the same time. So obviously this could be more complicated. Like if Bill takes a break for 20 minutes and then resumes, that would make this a lot harder. But we presume they work together. So they start at the same time and they finish at the same time as well. Okay. So you know the equation, right? Rate times time. So this is 1/4 times T, 1/4 times T over 1, which is just T divided by 4, right? Same thing here. This is 1/5 times T over 1, which is T divided by 5. Okay, so now we're almost done. We have this is the amount of work that Tina completes, the amount of the fraction of the lawn that Tina mows. This is the fraction of the lawn that Bill mows. Well, together, if they work together, what do? They mow one lawn, right? So I know I'm drawing two different lawns here, but pretend it's the same lawn, right? In this scenario, Tina's just doing everything by herself, and in this scenario, Bill's doing everything by herself. But now suppose they work together, right? So Tina starts over here, does that part of the lawn, and then Bill starts on the other end, mows that part of the lawn, and so together, this is sort of Tina's part of the lawn here. In fact, she does a little bit more than Bill because she works faster. And then Bill finishes this part of the lawn. And so, yeah. So essentially, they complete the entire lawn together. In other words, it's just one lawn. So what are we doing here? We're adding the fraction that Tina completes. That's T over 4. And then add to that the amount of work that Bill does, T over 5. And together, they have to mow one single lawn. Okay. So this is always going to equal 1 on this side, simply because they're mowing one lawn. They're doing one job, right? If you can say they're doing 3 lawns, then sure, set it equal to 3, but that's not going to happen here. Okay, so this is our equation, right? All we have to do is solve this equation to answer the question. We're looking for T. We're looking for the amount of time that they work together. Okay, well, this is a rational equation. It's not a proportion, right? This is not a proportion. How do I know that? Because the left side here, right? So On the right side, of course, we just have 1 over 1, right? That's a fraction. But on the left side, you have to be more careful here. The left side, all of this is not a fraction. It's not a single fraction, right? It's two fractions. You're adding two fractions. So you know how to add fractions. That's one way to reduce this down to a single fraction, right? You could do it that way. Here's the way I would prefer to do it. And again, that's just me. This is the way I like doing it. This goes back to section 7.6 when we're solving equations, rational equations, right? So in 7.6, we do this the old-fashioned way, right? Because we cannot cross-multiply here, right? Since this is not a proportion, you cannot cross-multiply because, well, there's no left side here. There's no numerator, there's no denominator. It's two denominators, two numerators, although, you know, coincidence that they happen to be the same. But they're definitely different denominators, so cross-multiplying is out here. It just won't work in this problem, right? Unless you add these fractions first, then you can cross-multiply. So that's, like I said, that's one way of doing it. The other way from 7.6 is to find the LCD, and there's only three denominators, 4, 5, and 1, so just multiply 4 times 5 times 1, and you get 20. So 20 is our LCD, right? And notice there's no t in the denominator, so there's no restricted values. So what I'm going to do is just take this equation, and let me just rewrite it one more time here. T over 4 plus t over 5 is on the left, and then 1 is on the right, right? So what do? We take the LCD, and we multiply left and right, right? Not top and bottom, left and right. Make sense? So by doing that, and then distributing the 20 here, we get 20t, sorry, that's a 0. Let me try that again. 20 times t divided by 1 times 4 plus 20 times t divided by 1 times 5 equals 1 times 20, which is just 20, right? So notice what we can do here. 20 divided by 4 is 5, so this is just 5 times t. And 20 divided by 5 is 4, so this is 4 times t. And that has to equal 20. Okay, sorry, that's a 4. And I think you can definitely take it from here, right? We got rid of the fractions. That was the whole point of multiplying by 20, to get rid of the fractions, to get rid of the denominators effectively. You know, well, I mean, they're still denominators, right? They're both equal to 1, but if they're 1s, we don't bother, right? So even though this is still a rational equation, we don't bother with the 1s, right? So we got rid of the non-trivial denominators here. So you know what to do. 5t plus 4t is just 9 times t is equal to 20. Divide both sides by 9. It's a 9. Cancel the 9s. So t has to be equal to 20 over 9 hours, right? So what's 20 divided by 9? Well, it's 2 and 2/9. You can write it as a mixed numeral that way. So it's just over 2 hours. In fact, 2 hours and 2/9 of an hour, whatever that is. But remember, I think they wanted this in minutes. So we have to do a little bit more math here. They don't accept hours. They want minutes here, right? So if they're being that picky, what do we have to do? We have to convert to minutes. Well, hopefully you remember that there's 60 minutes, right, in 1 hour, right? 1 hour is 60 minutes. So I can take the 20 divided by 9 hours, right, and multiply by, well, 1 hour is 60 minutes. And by doing that, notice that I cancel hours. So I just have minutes. Okay. So let's see. We have 20 times 60 is 1200 divided by 9. Calculator time. So 1200 divided by 9 is 133.3333. 133.3333, and so on. This is in minutes. So they want us to round to the nearest minute. right? So in other words, we can just lop off the decimal, or we can round. In this case, it's the same thing. So 133 minutes is the answer. So T, the amount of time it takes for them to work together, is 133 minutes. Or if you prefer, right, this is 120 minutes, which is 2 hours, plus an additional 13 minutes, right? So we can also say this is 2 hours and 13 minutes. Okay, and again, I'm not picky about that. Either 133 minutes or 2 hours and 13 minutes. And so that should answer the question. Right, so remember, 2 hours, 13 minutes, that's how long it takes for them to work together. 2 hours and 13 minutes. Which, right, should make sense here. Remember, they're working together. So if it takes Tina 4 hours to mow the lawn by herself and Bill 5 hours, right, to mow the lawn by himself, working together, they can almost cut their time in half, right? They can essentially do it in just over 2 hours, right? Almost, nearly 2.25 hours. But so that's the advantage of working together. When you work together, you cut the time, well, almost in half. Maybe not quite in Tina's case, but certainly less than half the time for Bill to do it. Bill would, half the time would be 2.5 hours. So that's the idea, right? You're saving time by working together. And if you get a third person to join in and help, you can do it in even less time, right? But I think in this case, we're going to stick with just this. So you'll notice that I did this a little bit differently than the way the book does it. If you'd rather do it the way the book does it, that's okay with me. It's maybe a little bit quicker, but conceptually, I find this a little bit easier to understand. It's very similar to the speed times time equals distance problem that we did. So I hope that helps.